one keeps coming. We have a new problem set, and we'll have our problem session as on Friday. The following week, I'll be on travel, so we'll try to think about what we're going to do with our problems later on. And we'll be scheduled either. We'll take over, or we'll have another alternative. All right. So last time we were really talking about the heart of what we, to this day, cannot completely wrap our brains around regarding quantum theory. Where at some level we wave our hands. And it has to do with the question of dynamics. Okay? And what we know in quantum theory is that there are two seemingly very different and distinct kinds of dynamics, which is to say, ways in which the state of the system should be changed as a function of time. In one scenario, which is easy to and rigorous to define, we say if we have a closed quantum system, as to say, if all the degrees of freedom, physical degrees of freedom, are included in the system, whatever it is, whatever the stuff is, particles, fields, what have you, that's all there is, then the evolution is unitary. Okay? And that followed from saying that if the state started in a pure state, it had to remain as a pure state. And moreover, and we're going to be a little bit more clear about what, as rigorous and quantitative, what we mean by a pure state later in this lecture. We loosely defined a pure state as a state where we have maximum possible knowledge about the system, but we'll be more precise about that in just a little bit. But because we have a closed system and we neither gain nor lose information, then a pure state stays a pure state, and therefore, and since the total probability is conserved, unitary maps preserve the norm, and the norm represents the probability, and there it has to be unitary. Okay? So that is clear, I think. And properties of this kind of evolution is, first of all, it's deterministic. That is to say, the state of the system at a later time is completely determined by the initial condition, because this map is something that comes from the physics. We haven't really talked about physics yet. We will, I promise you. The physics determines what this is, and if we know this, we know what the state is at a later time. So that's familiar kind of dynamics from classical physics, right? Newton's laws and trajectories, planets, what have you. Okay? And then we said there's some other kind of dynamic in the sense of another way in which the state should be changed between one time and another. And that is what we call measurement, whatever that is. And I'm being somewhat vague because it's hard to pin down what it is. But what I say is somehow if we learn the outcome of some possible alternative realization, then, for example, if we have something we're calling a meter, and it points after something happens up to one of the eigenvalues of some permission observable, then the state right after the measurement is given by this rule. Okay? And So in this case, this corresponded to a projected measurement. And we have there the projection operator operating on the state and then renormalized. Okay? And this was, if it was generally a degenerate eigenvalue, then there's an underlying assumption that this meter doesn't distinguish between the other eigenvalues of the mutually commuting observables. Otherwise, this would be a projector on the subspace associated with those other eigenvalues as well. Okay? And that happens with some probability. That probability is determined by the Born rule. Okay? That's the Born rule. So this kind of scenario is distinguished from this one in that this is not a closed quantum system. There's something we're calling the meter that is interacting with the system, and then it points after some kind of something happens, and it points along this direction. And after the measurement happens, we have this rule, which for the particular case of a non-degenerate eigenvalue means that the state afterwards is equal to the eigenvector corresponding to that eigenvalue that this meter points to. Okay? And again, that happens with this probability. And this kind of evolution is distinguished from this kind of evolution in two very important ways. One is that it's random. Okay? As to say, I can't predict with certainty, generally, unless the probability is 1 or 0, how the state is going to evolve, or how I should evolve the state. Depends which tense you want to use, the passive or the active. So it's random, stochastic. And the other thing is that it's irreversible, generally. That's to say, this is not a reversible map. I can't, from this, know what the pre-measurement state is. Whereas here I can, because this is an invertible map. So if I have the state at a later time, I can just invert it and find out what the state was at the initial time. So this is time reversible. And this is irreversible. Now, that might give some bit of a clue as to the question that really one would like to understand is, if if there is this kind of distinctly different type of evolution from this kind of evolution, we would like to know what physical situations do we apply this kind of evolution, and what physical situations do we apply this? Well, this we know. If we have a completely closed system, then we apply this. But as we said last time, why don't I just put all of this in a big box? In which case, everything is enclosed in my box, and isn't this then unitary? Okay, because we just said if everything is included, then the evolution is unitary. If we include all the quantum mechanical degrees of freedom that constitute the meter as well. So now there's this piece here that we haven't really addressed, and this came up in our discussion last lecture, in the notion that one way, the Copenhagen perspective, is that the meter is classical, and that there's somehow some kind of emergent phenomenon in our macroscopic world that we call the classical world, and the meter lives there. Okay? And we can't actually draw this box around it because the box doesn't live in the because the meter doesn't live in the quantum world. Now that's perhaps, I mean, to me, not completely satisfying because, you know, the meter is made up of stuff, atoms, molecules, solids, what have you. So, seems not fair to somehow bring it outside, say it's not a quantum object. But maybe there's something effective in some way that it's not, that's not completely a crazy kind of distinction to make. And that is the following, this question of irreversibility. So typically, when you learn about this, probably in some of your courses, you think about the measurement involves some kind of irreversible record. So the measuring device records the outcome. And this is done in some sense irreversibly. Now, this notion of irreversibility records, let me draw this six, records the outcome. Irreversibly. The question of irreversibility is something that we face in classical physics as well. Classically, the microscopic laws of motion are reversible. They're time reversible and variant. We just said we solve a set of differential equations when we do Newton's laws, or more generally Hamilton's equations of motion. And if I have a flow along a trajectory, and if I know what the point in phase space I am at some time, I can always reverse it and get back to the initial conditions. Yet we know in the macroscopic world, there's all kinds of irreversible things that happen, right? I mean, I don't see the chalk reassembling itself. So there's something that happens where, for all intents, even though we might say that microscopically the dynamics of these pieces of chalk are following, for all intents and purposes, Newton's equations of motion, effectively, it doesn't. And the reason is because what's happening is that we have so many degrees of freedom. I mean, what happened? Why doesn't that chalk reassemble itself? Well, what happened?
Because that's an extremely unlikely thing of happening, whereas it falling apart when you threw it like that is relatively likely.
Right, and why is it unlikely?
The entropy?
Well, the entropy, but what's actually happened? I mean, what happened is vibrations that when the chalk hit, it fractured and it caused the floor to vibrate, and those vibrations quickly dissipated into the floor. They're all there, but they don't reassemble because, as Keith suggested, for them to do that, it's just so unlikely for it to bounce in just the right way that it, comes back and comes back to my hand. that it just doesn't happen. The probability of that happening is just vanishingly small. It's not that it couldn't happen. It's just that it's so rare, and it's for all intents and purposes might be take, the age of the universe, and by that time, or maybe it's not even the age of the universe in this case, maybe it's some few millennia. By that time, we hope this physics building has adapted, but I don't guarantee that. So irreversibility is something that that is not microscopically true, but is effective, can be effectively true. Okay? And that's true in the quantum world as well, as we will see. So in the quantum dynamics, although microscopically are unitary, macroscopically need not be. Now, so this question, there's really a third kind of evolution. Which I will call irreversible. But predictable in the sense that there is a definite state that the system goes to after the evolution. And this is what we would call open quantum system dynamics. So maybe there's my spin here, but so this is my system, but it's open to the world, which we might call the environment. So in that case, I can have the situation, for example, where a spin relaxes, dissipates, and might decay, for example. And the decay is happening because some dissipation happens. This kind of evolution is not unitary, because we're losing information here. Okay? So, what Bohr would say is that the effect that the measurement happens when the device is sufficiently macroscopic that there is some kind of irreversible interaction that happens, and the measurement is recorded, and just like the chalk that's shattered, it, for all intents and purposes, is irreversibly measured. Okay? And that's where the classical world is, where you have that level of many, many, many degrees of freedom that, for all intents and purposes, we can call it classical, because it has that irreversibility. Yeah?
What if we make a microscopic meter?
Well, that's a good question. Well, and people do try to do that, all right? So, it's the right question to ask. Where is that boundary? At what point does this become sufficiently macroscopic that we can call it a meter, and when is it? And experiments have been done in this sense, where we try to, say, measure a single atom with a single photon. And there are properties that we can see in that kind of things which are more akin to this, where I put in the photon in that and call that the closed system, and situations where are more akin to this. However, and this is a big however, this doesn't really solve the problem. In the sense, as we'll see, that this is what I said is a third kind of evolution. It's not this. In the sense that we can talk about dissipation, we can talk about irreversibility, and that would have to come out of taking a unitary evolution of the whole thing and then somehow losing some information to the environment, sort of marginalizing our probability distribution over the stuff we don't know about. But that's never going to give me a jump. That's never going to give me another pure state. This went from one pure state to another in a completely random way. This goes from a pure state to something where I'm impure. Actually, we don't say impure, we say mixed. So dissipative dynamics isn't the same thing as measurement. So whereas the Bohr picture of this might tell us, okay, these are the kinds of interactions we want to call measurement. The interactions with the meter, where the meter is sufficiently macroscopic that I can call it classical because it irreversibly records the measurement outcome. It is insufficient to explain how you can't derive this from this. So, what do we say? Well, there's only sort of, in one sense, one answer left, and that is me. Me, me, me. The observer. That in some sense, and this came back to this question of what is collapsing? So what we discussed a little bit last lecture is this notion that we should think about the state as a state of knowledge. The state, psi. And that the measurement rule is like Bayesian update. So you remember we discussed last lecture that if I have a probability distribution classically, and I learn something new, then I should update my probability based on what I learned. And in some sense, this rule, the measurement rule, is that. Okay? So this perspective is what's called cubism today. It's a way of thinking about quantum mechanics, quantum Bayesianism. It's a takeoff on Picasso. And it's a perspective on quantum theory that kind of has its origins here at UNM. It's was something that came out of the group of Carl Caves and is really being developed and pushed forward by Chris Fuchs and Rudiger Schock. Chris was Carl's student, and Rudiger was his postdoc some years ago, which basically says that quantum mechanics is really just a theory about the observer being able to make predictions. And that what is happening, the state is not a physical object, it's just about what we know. And when you learn something new, you update it. There's no mystery there, okay? Physical interactions happen. The meter and the system interact. They could do so irreversibly. But I don't update the state until I look at it. Okay? Now, here's where I think this still doesn't really answer the question. This is like, I look at this a little bit like Gödel's theorem in mathematics. There are formal questions you can pose within the formal system that are just not answerable within the system itself. Okay? Here is the issue. Quantum mechanics is a meta theory. What do I mean by that? It means that when we have a set of rules that are self-consistent within the theory itself, we have states and we have unitary evolution. That's all perfectly clear, self-consistent. You don't have to ask questions, is this or not? Is it? It just is the rule within the formal structure of the mathematics itself. But what is different about measurement is that the measurement is stochastic. So the basic rules of quantum are deterministic. Measurement outcomes are random. Where does this randomness come from? That's the fundamental question that continues to baffle us. Well, we did the perhaps failed experiment yesterday, so I'm going to do it a little bit different now. You found that mic.
How about
That one. Okay. So, here we go. The chalk is in one of my hands. Which hand is it? Your pocket. Well, it's in this one. See, everyone? Stephen, check it out. All right, back to the right. Okay. Now, that was random. But that's not surprising. It's random. So the way we think about randomness is that randomness arises traditionally or classically because we have incomplete information. The information was there, we just didn't have it. Okay? And so there was information that was hidden from you. But once you learned it, then you had a particular result. But in quantum theory, we can have maximum possible knowledge. And yet, possible. And yet, random. Now, of course, it's hard to know whether that's true or not, and that's been one of the great triumphs of the last few decades, last maybe half century, coming up on that kind of scary, don't hold me that bad. I mean, it's very natural to think the reason that random results are seen is because we just don't know everything. And if we just had that rest of that information, we'd be able to predict what would happen. So, you know, when you flip a coin, it's only random because of exactly how you flipped it and what the air pressure was. But if you knew all that, you could predict the tumbles and whatnot. So, intuitively, we think about randomness as coming from incomplete knowledge. But what we know now is that so Einstein, of course, famously believed that this had to be the case, that the randomness that we're seeing in quantum mechanics is of this sort. There were hidden variables that were there, that were telling the photon which slit to go through. But they were just hidden from us. And if we had access to them, we could predict which way the photon would go through the beam slitter. That's natural. That's what you think. And what we have come to learn is that if there are hidden variables in quantum mechanics, they can't be local to the particle themselves. They must in some way be distributed non-locally, and things at one side of the universe affect the other. And that's just that's a completely inconsistent perspective on physics. So we just give up hidden variables. We say, this is why quantum, so let me come back to this when I'm talking about meta, because I haven't quite defined that yet. If measurement outcomes are random, and the basic physics is deterministic, and the randomness is not coming from just missing information, then we have to import something outside quantum mechanics. To extract measurement outcomes. Because we can't get quantum mechanics to evolve into random outcomes. So we have this theory, and then we have this layer on top of quantum theory that's meta. Outside the quantum theory itself, that doesn't obey the laws of quantum mechanics, that somehow extracts these random things. In the Copenhagen interpretation, the meta thing was the classical world and the classical device. And you reeled in the classical device, you don't tell me what devices are classical or not, and where that border is, if it's 3 photons, 4 photons, 5 buckyballs, but you just say somewhere it's the classical world and it's outside the quantum world and it extracts the results. In the cubism perspective, it's you, the observer. the person, the human being, your consciousness, what you know. What do you think about that perspective?
Self-centered.
I am, but yeah. I'm not saying I adhere to this perspective. What the Cubists say, really frankly, is that your experience is outside the description of science itself. It just makes that statement. It will be impossible. You cannot, it's a particular logical reasoning. And it basically says that, I mean, so it's me, but maybe me over here, you know, should be inside the quantum system too. So it's not just about me looking at the meter. So here's an experiment that I want you to think about. Suppose I have a single photon, and that single photon is put through a beam splitter. And that beam splitter now sends one path to this side and one path to this side. Well, how should I think about that? I could think about that as, you know, my eyes and my brain are physical stuff. There's retina A and optic nerves and made of stuff, and there's a quantum correlation between the photon hitting there and some activity maybe in this bald head, and the photon going here and some other activity. And from the point of view of quantum theory, well, maybe there's some dissipation in there, but there's no way that that's going to be one or the other. Quantum theory of all the nerves in my head aren't going to make a jump. So just by making it a human being rather than a meter, does that solve the problem?
It just moves the problem.
It just moves the problem there. That's what I'm saying. The problem, unless you cut the cord and say, this is outside. I mean, in Cubism, answer the problem by just stating. And in some sense, it's self-consistent because there's no way, because my experience, there's no way for you to actually test that because you don't know my experience. You have your experience, but you're inferring about mine, right? So it is a logical perspective, but it's somehow maybe not completely satisfying. It puts your experience meta. Whereas the Copenhagen interpretation puts the classical measuring device meta. I think that's completely unsatisfying. Because the classical measuring device is stuff. Maybe your experience is somehow different. I don't know. Moreover, if you want to take this Bayesian perspective completely, for me, here's a problem with it. I mean, when we learned that the chalk was there, so when we say quantum state is a state of knowledge about what? In this case, you know, whether the chalk, it was knowledge of whether the chalk was in my right hand or in my left hand. And you learned that when you saw the answer. But when you measure the photon, you're not learning that it was in this path or that path, because we just said that that's not really consistent with experiments you can do. So it's still, we're in this goidal circle. We just keep pushing the problem out. And all I'm saying is, at the end of the day, what we have to do is accept this. We should continue to think hard about this problem. You know, every generation has made further progress in distilling down the essence of this problem and doing the kinds of things that Adrian was suggesting of, can we really push these boundaries, make the meters more and more quantum and see what happens? Grow them macroscopically, understand, is there a quantum classical boundary? But at the moment, I don't think we're there. I hope one day, before I die, I will have this epiphany and understand this, but we're not really quite there yet. All right. Given all of that, so now, you know, we're going to return, I should say, to some of these questions about local hidden variables and so forth in the foundation of quantum mechanics at the end of the semester. We're going to circle back when we have a little bit more of the formalism of physics to address these questions and understand why I can't assign local hidden variables to objects. Why is that just inconsistent and purely wrong? But for now, we'll just accept that as true. Okay? So let's just talk then, continue about an example of, well, what is an example of a measurement? Okay? So let's talk about the most familiar and clearest example of a quantum measurement. The famous Sternberg clock apparatus. Okay, so you're familiar with this. Let me just remind you. So the question is, I want to measure the spin of, for example, silver atoms. Okay? Silver atoms have a spin 1/2 as it comes solely from the electron. So how is it done? I want to measure that. Well, what's done is, so I have an oven. There's some sodium, very dilute sodium vapor here, and the sodium atoms is collimated through some opening, and I have a beam of sodium atoms that comes out of this oven. And then I pass it through a region with a inhomogeneous magnetic field. So the magnetic field, we have this north and south pole, and that has some gradient in the strength of the magnetic field. The field lines are closer together at this point than here, so the strength of the field is stronger up here than there. And what one finds is that the beam separates. Into two beams. Right? And the way that this is interpreted is by the force that is given to the sodium atoms, the kick either up or down, that is given to the sodium atoms that depended upon whether they were spin up or spin down. Right? So, what we know from classical physics is that the force on a neutral particle with a magnetic dipole moment, well, the energy is minus mu dot v. And then the force is minus the gradient, right? So the force is the gradient of mu dot v. Now, let's call the direction of the gradient, let's just call that the z direction. The magnetic field strength is varying as a function of z. Okay. So this is equal to, in this case, mu z dv d by dz of the magnitude of z in the z direction. That's all I care about. All right, because the gradient is in that direction. So, fine. So this is the magnetic dipole moment. Now, quantumly, what we do is we say, in fact, that the magnetic moment, magnetic dipole moment, is proportional to the spin. And in fact, that proportionality constant we can find by measuring how much this deflection is. And what we find is that it's equal to twice the Bohr magneton times the spin, or spin 1/2. Okay? So this is the Bohr magneton. Which is E h bar over 2 the mass of the electron, C, in my favorite Gaussian units. Yeah?
Is the 2 something special, like for an electron?
It is. It is for, that's the so-called G factor. And we'll review all that stuff again later. But you should have seen it. We'll review it. Now, of course, what we say quantumly is, in fact, the spin observable is an operator. Okay? So this is really a force operating. This is, well, it's not classically, it's not, but quantumly it is. Okay? We're treating the magnetic field here as a classical field. I'm going to ask the question, is that right or not? But it's the quantum nature of that would not affect this experiment. Okay. Okay, so that means that, and that spin is equal to h bar over 2 times the Pauli matrix. So this is equal to UV. Oh no, I'm sorry, this should be over h bar. Yeah, that's got to be right. Now it's got the right units. And that's equal to h bar over 2 times the Pauli matrices over h bar. So what we have here then is that the quantum force, oh, and it's an electron, so it's got to be minus. Is equal to signs are off here. It doesn't really matter. It just means that my pictures are backwards. So let's see what we got here. We have minus mu d, the gradient, or the change in the magnitude of b times sigma c. Mu is equal to Okay? And this is all in this direction. Oh, I see why this gradient is actually negative, because it's pointing down. That's why I did keep that. Okay. So, all right, so that's the force. And what we see is that because if the spins here are spin 1/2, then there are two possible trajectories. The trajectory associated with the spin-up atoms, which go here, the spin-up along Z, and the trajectory along the spin-down atoms, which go along there. Okay. And if I were to put a screen here that absorbs these silver atoms and makes a little black spot on the screen, what I would see is I would see two spots. I'd see a spot here and a spot here. And we would say that we've done a measurement. And if it lands in here, we would say it's spin up. And if we lands in here, we'd say it's spin down. Okay. So here, this is an example of a measurement. Now, is this a projected measurement? Yeah, in some sense it is. Because we can say that it's projected because the probability to find spin up or spin down, or I should say it this way, to find up or down,
Probability?
the probability is uniquely given by the eigenvector. It's not quite of the sort that we described over there in terms of the post-measurement state. We said after the measurement, the state of the system is in that eigenvector corresponding to the eigenvalue we just measured. The reason is the sodium atom's gone. I can't, it's been absorbed, it's done a chemical reaction, I can't do another measurement on the thing. So it's not, although the probabilities of being here or there can be calculated by the Born rule with a projector associated with that is to say, the probability of being this, so that probability of being that is the expectation value of the projector. And this probability is equal to the expected value of that projector. That's the Born rule. The post-measurement state is not, well, it's no longer a sodium atom, it's something else.
We're working with silver.
I'm sorry, silver, yeah. All right, so, all right, well, that's fine. Like I said, it's really hard to do a projected measure. What about this? Suppose I come over here, and instead of putting a screen, what I'm going to do is I'm going to put a blocker here that blocks that beam. Is that a projective measurement? Well, kind of. Again, it's not exactly of this. I mean, what is true, these atoms are gone. The silver atoms are, being absorbed by this blocker, and they're gone. But these guys are free. And since I know that the way in which this beam moves is consistent with this force, then I can say that with certainty the atoms that went through, that are in this path, are spin up. And so the post-measurement state, regardless of what came out of this oven, which I haven't even explained yet what that state is, but regardless of what it is, I can say I projected the silver atoms into this state. Okay? It's not quite a projective measurement where I kind of was able to say, well, I got this or that, and after the measurement, it's projected into that guy because I blocked this guy. But still, it has some of the flavor. Okay? And how could I check that, in fact, this was a projection onto this?
I'll run it through the same thing again.
Yeah. So I can run it through another Stern-Gerlach apparatus. And what I'll find is, in contrast to this, what I'll find is I'll just get, in that case, just one beam. I do a repeated measurement, and I'll get only one result, because it was definitely in that state. And atoms that are spin up along Z get deflected along that direction. Okay? Of course, and this will be very hard for me to draw, but I'll try. I hate drawing perspective. Suppose that I put the second Stern-Gerlach apparatus along the x direction. So that's the x direction. Okay. Bear with me. And what you're going to see is two beams. Okay? Those two beams correspond to, let's call this the x direction, spin up along x, and spin down along x. This is what I mean to say I have a pure state. That pure state is I have the maximum possible information I can have. It's that state, spin up along Z. But nonetheless, even though I have complete information about the system, there are measurements I can do which don't have definite outcomes. That's the essence of the quantum world. That's what distinguishes it from the quantum world. In the quantum world, if you have complete information, you can predict everything about it. Whereas in the quantum world, you can't. Now, we know also the probability where the thing is going to end up here or there. And that's given by the Born rule, right? Now let me ask you another question. Is this a measurement? Well, it sort of depends. Suppose I have some way of making an atomic mirror, which exists. And I can take these two beams and bounce them back with some steering magnets. These two beams come back together. Okay? So the two beams separate, they bounce, and they get recombined. And now I put them through another Stern-Gerlach apparatus along the z-axis. What's going to happen? I'll have one beam again.
So they don't lose that.
So it kind of depends how good I did this experiment. These two possibilities remain in superposition. They have coherence. They can interfere if they are in principle indistinguishable. Just like this, you can think about the Stern-Gerlach apparatus. In fact, the Stern-Gerlach apparatus is formally equivalent to a polarizing beam splitter in optics. So this is an analogy. A polarizing beam splitter. In a polarizing beam splitter in optics, you go through you go one direction or another depending on what your polarization is. So this is like a beam splitter. Split the beam. And if you recombine the beams, and the two beams are coherent, they remain coherent, they will interfere. So just because I separated it doesn't mean that I've done a measurement. Of course, if I scatter a photon, I can look at it and see, and a photon scatters, and I see it, then I've done a measurement. Because the photon distinguishes the two paths. And if the two paths become distinguished, then they no longer interfere with one another. They lose their coherence. Coherence means the potential to see interference. It goes back to this issue of the measurement having to have some aspect of irreversibility in it. Okay?
What if you put the Stern-Gerlach where that mirror is, or one of those atomic mirrors, like,
You put it here?
yeah, it'll split back up into two different.
It will.
Okay.
It will. I mean, then you'll see it spin up and spin down along Z. Absolutely.
Or along X or along Z.
I mean, as Adrian said, if I put it along Z, this is spin up along X.
Okay.
Spin up along X is this superposition of spin up along Z and spin down along Z. And this beam is split in two.
Oh, okay.
But the fact that I have these two beams and I've combined them in such a way that I couldn't tell, if there was no way to tell, if I had to align the interferometer perfectly, such that there's no way that the interferometer can tell which path it came from. Then, as we said in the very first lecture, if I can in no way distinguish the two alternatives, they interfere. Keep your energy.
I was just going to say that putting the SG at the top is the same as bringing the blocker into the bottom one.
Yeah.
You mentioned
It is, of course, you could, if everything remains coherent, then I could try to recombine all those three beams in some way and see interference between the different alternatives.
So, is there some sort of phase shift with the?
I could do that too, and I could, try to phase shift this such that I can think about this analogous to our, remember we drew in the first lecture, we drew the optical interferometer, the Mach-Zehnder interferometer, right, where we send something through a beam splitter, down, store, off, and what we found is that if we aligned it perfectly, it went this way, right? But I could phase shift it, and then sometimes it would come out this way. Similarly, there are two outcomes here, and which outcome is depends on how these two paths interfere with one another. So the general state that I see here is some superposition C plus and C minus between those two paths. And what that is, if it started out in this case as 1 over root 2 and 1 over root 2, actually this is x, doesn't matter. But I could try to phase shift one or the other because I can get the v to go the other way. Just like here. All right, let me remind myself where I was headed with this. Oh yeah, one last thing. So let's let me go back to this picture. I'm sorry I'm using the same word over again, but I'm too lazy. So here's my apparatus. Okay. Suppose that I wasn't a very good experimentalist, and I didn't calculate this force well. I didn't do my modeling properly, and I didn't know where to put the screen. So I decided I'm going to put the screen right here, well before those two beams separated from one another. So what I'm going to see, if I were to make a histogram of the counts, I wouldn't see two spots. What I'd see is this spot, that's two spots that's not, they're not resolved, right? So I can think of, I can try to fit and say, well, there's, there's this Gaussian over here, and this Gaussian over here, but they're not separated from one another. Okay? So I've measured the spin in some way, but I can't distinguish perfectly the spin up spot from the spin down spot. They overlap with one another. Is this a projected measurement? No. I can't answer yes or no, are you spin up or are you spin down? When they were resolved, I could. I'd say the ones in that spot were spin up. The ones in that spot, maybe the ones out here I can, but in here there's some tails that overlap. So I can't ask, I can ask questions, but sometimes my answer is maybe. So projected measurements are yes or no questions. Are you spin up or are you spin down? Because the way we see that mathematically is that the eigenvalues of a projection measurement or a projector are 0 or 1, true or false. Okay? But this kind of measurement has maybe in it. And so in order to determine, are you in this, as an experimentalist, what would I do? I would fit this data to two Gaussians. And if it lies in this Gaussian, I call it spin up. And if it lies in this Gaussian, I call it spin down. Or I call it the plus result or the minus result. But in fact, it doesn't really, can't say. Sometimes it'll give me a maybe. So there are these two alternatives corresponding to these two Gaussians, but they're not projectors. They're something else. And what they are positive operators. So this alternative, this is alternative 1. Or the alternative plus, and this is alternative minus. Those two alternatives, they resolve the identity. And I associate a positive operator corresponding to these two overlapping Gaussians to each of them. And my probability of seeing up, or this alternative, is the expected value of this. And the probability of seeing minus is the expected value of this. It's the generalization of the projective measurement. This is an example of what's sometimes called a weak measurement, because I haven't really projected the system onto one or the other. I've left things a little bit uncertain. And this is, of course, a general POPM. Yeah?
This kind of maybe even suggests that a weak measurement could be made into like a strong measurement.
What do you mean by that?
That this is a weak measurement, but by putting the screen a little farther,
Oh, yeah,
you can
absolutely,
make it a strong,
absolutely.
I'm not sure that's called a strong measurement.
It is exactly what it's called. So a strong measurement is the same thing as a projective measurement. So there's a complete continuum here. You know, at this point, I've learned nothing. The two peaks are not resolved at all. And as I move the screen farther and farther away, the measurement becomes stronger and stronger and stronger.
So there's probably cases where you can't do that though. Does it always become like a weak measurement?
Every measurement, physical measurement, happens over time in some sense. Here the measurement, the physical process that allowed us to do the measurement was the force exerted on the trajectory of the atom. And that it takes time for that force to accumulate in order to separate the two alternatives. So it's always the case, always, that if you don't give the meter enough time to resolve the different alternatives, the measurement will be weak. So this is an example that is not discussed. Have you seen this example before? No, I mean, but it's kind of obvious, isn't it, that this is not a projective measurement. And most it's very hard to do a projective measurement in quantum mechanics. Most measurements are not. Now, one of the problems in homework is to see an example of that and see the mathematics of that. We discussed that at our problem session. Now, before I quit for the day in this lecture, I just want to ask you one question. What is the state of the spin coming out of the oven?
Don't know. Is it a superposition? Coherent?
Good. So yeah. So those are two good answers. Two good possible answers. We don't know. And it's a superposition. So let's think about those two alternatives. State coming out of the oven. So one possibility is to say, well, we made a measurement along Z. So we don't know. Which would say, for example, if we'd have complete no knowledge, it's completely random, we would say it's 50% spin up along Z, and 50% spin down along Z. Another possibility is there is a quantum superposition of up and down along Z. So that would say the state of the system was 1 over root 2 spin up along Z, and with some phase spin down along Z. Now, good question, Z. Same thing, I guess. Certainly, we couldn't distinguish those two things if we did this experiment, right? If we did this experiment, we're going to see 50%, you know, if we did a good measurement, stronger measurement, we would see equal intensity of these two peaks, and 50% of them would go up and 50% would go down. But what if instead I measured this along the x direction? Well, if this phase were 0, let's say we did this, said this was the superposition. Okay, this state and this state would show the same measurement results for this. But suppose instead I measured this along the x direction. Well, what would I find if the state were this?
It would all go in plus x.
Right, because this state is equal to plus x. I would see one beam. Whereas in this case, I would say it's half of the time it's spin up, so the probability of seeing up along x is that, and half of the time it's spin down along z. So the probability of seeing spin up along x is that. So that's the 50-50 mixture. And what's that probability? Well, this is a half. This is a half. So this overall is a half.
But
So this is the right answer. This is the wrong answer.
because why would x be preserved, be preferred over z? I mean,
It wouldn't.
You could just relabel that.
Exactly. So that's why this is the right answer. It's always going to be, no matter what direction if it's an oven, it's a completely random spin, then no matter what I see, I'll see two beams, 50-50. This state is not a pure state. This state is what we would call a mixed state. A mixed state, as we will discuss next week, is a situation where we're actually missing information. We don't know how the spin was spit out of this oven, as Stephen suggested. And because of that, we need to average over missing classical information. Quantum mechanics needs to allow us to include missing classical information as well. So the most general states of the system are ones where I don't have complete information about the quantum system. There's temperature here. There's thermal randomness that's different from this intrinsic quantum randomness.
Is it kind of hard for particles in that environment to maintain coherence?
Absolutely.
So it just comes out.
It comes out as a completely incoherent mixture. It's analogous to polarized light versus unpolarized light. we will pick that up next time.